An induction generator or asynchronous generator is a type of alternating current electrical generator that uses the principle of induction motor to produce electric power. Induction generator operate by mechanically turning their rotor faster than synchronous speed. A regular AC induction motor usually can be used as a generator without any internal modification. Induction generators are useful in the applications such as mini hydropower plant, wind turbine, or in reducing high pressure gas stream to low pressure. Induction generator usually draw its excitation power from an electrical grid. Now we will study about how induction generator works. Consider an AC supply is connected to a stator terminal of an induction machine. The rotating magnetic field produced in the stator pulls the rotor to run behind it. The machine is acting as a motor. Now if the rotor is accelerated to the synchronous speed by means of a prime mover, the slip will be 0, hence the net torque will be 0. The rotor current will become 0 when the rotor is running at synchronous speed. If the rotor is to rotate at a speed more than synchronous speed, the slip becomes negative. A rotor current is generated in the opposite direction due to the rotor conductor cutting the stator magnetic field. This generated rotor current produces a rotating magnetic field in the rotor, which pulls onto the stator field. This causes a stator voltage which pulls current flowing out of the stator winding against the applied voltage. Thus, the machine is now working as an induction generator. Induction generator is not a self-excited machine. Therefore, when running as a generator, the machine takes reactive power from the AC power line and supply active power back into the line. Reactive power is needed for producing rotating magnetic field. The active power supplied back in the line is proportional to the slip above the synchronous. Now we'll discuss about the excitation of an induction generator. Induction machine always consume reactive power regardless of whether it is operating as a generator or motor. A source of excitation current from magnetizing flux, that is reactive power, for the stator is still required to induce rotor current. This can be supplied from the electric grid, capacitor bank. Self-excited induction generator. It is clear that an induction machine needs reactive power for excitation, regardless of whether it is operating as a generator or motor. When an induction generator is connected to a grid, it takes reactive power from the grid. But what if we want to use an induction motor to supply a load without using an external source? A capacitor bank can be connected across the stator terminal to supply the reactive power to the machine as well as to the load. When the rotor is rotating at enough speed, a small voltage is generated across the stator terminal due to the residual magnetism. Due to this small generated voltage, capacitor current is produced, which produced further reactive power for magnetization. Now we will discuss about the torque speed characteristics of induction generator. The torque speed characteristics of a 3-phase induction generator for all ranges of the speed are shown below. In an equivalent circuit of induction generator, the mechanical shaft load has been replaced by a resistor given by R mechanical equal to R2 by S into 1 minus S. In an induction generator, the slip is negative. Therefore, the load resistance R mechanical is also negative. This shows that the load resistance does not absorb power but start acting as a source of power. It starts supplying the electrical energy to the supply means to which it is connected. The output of the induction generator depends upon the following factors given below: the magnitude of the negative slip, speed of the rotor or how fast the motor drives above the synchronous speed in the same direction, rotation of the motor when it is operated as an induction generator. It is clear from the torque speed characteristic of induction motor that maximum possible induced torque occur in the generating mode. This torque is known as pushover torque. If the torque becomes greater than the pushover torque, the generator will be overspeed. Now we will discuss about the use of induction generator. Induction generator are often used in wind turbine and some micro hydro installation due to their ability to produce useful power at varying rotor speed. Induction generators are mechanically and electrically simpler than other generator types. They are also more rugged and require no brass and commutator. Limitation. An induction generator connected to a capacitor system can generate sufficient reactive power to operate on its own. When the load current exceeds the capability of the generator to supply both magnetizing reactive power and the load power of the generator will immediately cease to produce power. This load must be removed and the induction generator restarted with either DC source or if present with residual magnetism in the core. Induction generators are particularly suitable for wind generating station as in this case speed is always a variable factor. Unlike synchronous motor, induction generators are load dependent and cannot be used alone for grid frequency control. Now let's see this example. Consider the use of 10 HP, 1760 revolution per minute, 440 volt 3-phase induction motor as an asynchronous generator. The full load current of the motor is 10 ampere. The full load power factor is 0.8. Find the required capacitance per phase if capacitors are connected in delta. We know that apparent power equal to root 3 E into I. Putting the value of E and I, we will find the apparent power is 7612 volt ampere. We know that active power equal to apparent power into cos theta. Putting the value of the power factor, that is cos theta 0.8, we will find that active power equal to 6090 watt. To find the reactive power, we will multiply apparent power with sin theta. So multiplying it with sin theta, that is 0.6, we will find that reactive power equal to 4567 watt. For a machine to be run at asynchronous generator, capacitor bank must supply the minimum 1523 watt per phase. Voltage per capacitor is 440 volt because capacitors are connected in delta. Capacitor current will be reactive power divided by its voltage per phase, that is 3.46 ampere. Capacitor reactance per phase equal to voltage per phase divided by current per phase, that is 127 ohm. Now we know that capacitive reactance Xc equal to 1 by omega C, therefore C will be 21 microfarad. If the load is also absorb reactive power, capacitor bank must be increased in size to compensate.